In this video, I want to mention some properties of line integrals. The first property that we're going to look at deals with the orientation of a curve. We say that a curve is oriented if it goes in some direction. So let C be an oriented curve. So I might have something that looks like this, and it goes in some direction. We define negative C to be the curve oriented in the opposite direction. So we would take the same curve, except it would point in the other direction. One of the properties of a line integral is that the line integral of a function over some oriented curve is the same as the line integral of the same function over the curve oriented in the opposite direction. So no matter how the curve is oriented, you get the same line integral. We'll demonstrate this property by looking at an example that we did in our last video. So again, we want to find the area under the surface z equals x times y on top of the line segment from 1, 2 to 3, 1. Last time we came up with a parameterization for this line segment that started at 1, 2 and ended at 3, 1. This time, we'll parameterize the curve starting at 3, 1 and going to 1, 2. So we're doing the opposite orientation. So in this case, the curve has direction -2, +1. This time, the point that we'll start with is 3, 1. So our parameterization, r of t, is going to be 3 minus 2t, 1 plus t. And again, our t goes from 0 to 1. So let's find r prime again. R prime in this case is going to be -2, 1. And the magnitude of r prime is still the same. Square root of -2 squared plus 1 squared is square root of 5. So this time our line integral will look like integral of x times y, so that's 3 minus 2t times y, that's 1 plus t, times magnitude of r prime, that's square root of 5, dt integrated from 0 to 1. Pulling out the square root of 5 and multiplying out the integral, we have 3 plus t minus 2t squared dt. Computing the antiderivative, we have square root of 5 times 3t plus 1/2 t squared minus 2/3 t cubed, evaluated from 0 to 1, which is square root of 5 times 3 plus 1/2 minus 2/3. And if you simplify this, you again get 17 square root of 5 over 6, which is the same as we got last time. So again, this confirms this property of line integrals that no matter how you orient the curve, your line integral will always be the same. The second property of line integrals that we'll look at is as follows. If C is a piecewise smooth curve with pieces C1, C2 through Cn, then the line integral of f over c is the sum of the line integral of f over each of the individual pieces. Let's look at an example where we use this property. So in this example, we're asked to evaluate the line integral of 2x minus y over a curve c, where c starts at the origin, goes along the curve y equals x, then goes clockwise when it meets the circle x squared plus y squared equals 9, then goes back to the origin when it meets the line y equals -x. Let's start by drawing our curve. It starts at the origin, then goes along the line y equals x, then it meets the circle x squared plus y squared equals 9, and then once it meets the line y equals -x, it goes back to the origin. So our curve looks like this, where these intersection points are 3 square root of 2 over 2, 3 square root of 2 over 2, and over here I have -3 square root of 2 over 2, 3 square root of 2 over 2. So our curve C can be broken apart into 3 pieces. C1 going along the line y equals x, C2 going along the circle x squared plus y squared equals 9, and C3 going along the curve y equals negative x. The property tells me that I can calculate the line integral over C by calculating the line integral over the individual pieces, then adding them up. So let's find a parameterization for each piece. For C1, I have the parameterization r of t equals t, where t goes from 0 to 3 square root of 2 over 2. R prime of t would be 1, 1, so the magnitude of r prime of t would be square root of 2. Our second curve, C2, would have parameterization r of t equals 3 cosine t, 3 sine t, where t goes from pi over 4 to 3 pi over 4. And the magnitude of r prime of t in this case will be 3. Lastly, C3 will have parameterization t negative t, for t values going from negative 3 square root of 2 over 2 to 0. Again, here r prime of t will be 1, negative 1, so the magnitude of r prime of t will be square root of 2. Our line integral of 2x minus y ds over the curve C is going to look like the sum of the line integrals over each piece. So for the first piece, I have the integral from 0 to 3 square root of 2 over 2 of 2 times x minus y. So that's 2t minus t times magnitude of r prime, so that's square root of 2 dt. On the second piece, I have integral from pi over 4 to 3 pi over 4 of 2x, so that's 2 times 3 cosine t minus y, so that's minus 3 sine t, times magnitude of r prime, so times 3 dt. And then lastly, on C3, we have integral from negative 3 square root of 2 over 2 to 0 of 2 times t minus negative t times the magnitude of r prime, so that's times square root of 2 dt. I'm not going to go through how you calculate each of these individual integrals. I just wanted to illustrate that you can use this property to break apart a complicated line integral into more manageable pieces. And that's where I'll end this video. Thanks for watching.